So if any of you have ever noticed, on my chair I have these little plushy pillows, and they are not just for cuteness, they're actually for learning. So I spent way too much money on these, but this is the first of the ones we will learn. It has a hair on it. And this is the normal curve. So no longer are things just bell-shaped. We're going to start learning about what the normal curve is, and this is how they standardize all SATs, ACTs, any standardized test takes your scores and puts them into a normal distribution so that they can accurately give you your percentile in comparison to everyone else. So we're going to learn how to take scores and actually standardize them to create a Z-score for certain tests and sets of data.
A what?
A Z-score. A Z, yes. So facts about the normal curve: it is bell-shaped, symmetrical, unimodal, looks exactly like this, and it never, ever, ever changes the shape. It looks identical to this. It is always centered at the mean. So the middle point is your mean, or the average, and then it goes out about 3 standard deviations on each side. So I'll show you kind of in a minute what it looks like. We're going to skip the calculator part for right now, and we'll come back to it with our new notes. 2 facts that you do need to have memorized or understand, just the conceptual part of normal curves, is that as the standard deviation increases, the curve flattens and spreads. If the standard deviation decreases, it's going to be tall and skinny. So let me show you 2 examples of different normal curves. So it's always centered at your mean. Here's 2 different examples. Shapes are the same, but the width can change. There are about 3 standard deviations on each side. That's about the width. And if you have a larger standard deviation, say this were like standard deviation of 10, and this were a standard deviation of 2, then this one is going to be much wider than the standard deviation of 2. So kind of makes sense, but just wanted to give you a picture visually of what that looks like. Going to skip this part. So the first fact about a normal curve is, yes, it does go 3 standard deviations out on each side, but within like 1 standard deviation, 2, and 3, there's actually a percentage of data points that fall within those areas of your normal curve. So if you go out 1 standard deviation on each side, so looking at my picture, my mean is in the middle. If you go plus or minus 1 on either side, that actually contains 68% of your data. So we take a test. I convert everyone's scores to be normally distributed. And if it were following the normal distribution rules, let's say the average was an 80, and the standard deviation was 4 points. So that means I subtract 4 and I add 4. If this were correct and it were a normal distribution, that would mean 68% of you, so almost 70%, scored between a 76 and an 84. Okay? The next one is if you go out 2 standard deviations. Hold on a second. If you go out 2 standard deviations, 95% actually fall within 2. So that would mean 95% scored between a 72 and an 88. And then the last one is 3 standard deviations. That is 99.7%. So that virtually covers every single person. There's 0.3% that are left out that scored between a 68 and a 92. Then you've got these percentages out here 0.15 on each side, percent. So that is called the empirical rule. I will say you do need to memorize those three numbers because they show up a lot on multiple choice questions. But when you're finding, which is what I passed out to you like on our notes, when you're calculating certain percentiles and things like that, you're always going to be able to use your calculator. So the big takeaway from the empirical rule is just to understand 68, 95, 99.7, and just understand that that's like plus or minus 1, plus or minus 2, plus or minus 3 standard deviations out. So that's kind of the big picture, but I'm going to show you more how to interpret that. So I'm going to skip this slide because I have it on the next one. Yes?
Where did we get the values on the bottom, like the 7, 6, and the 84?
I said that the standard deviation was 4. So when the standard deviation is 4, I'm going to go up 4, up 4, up 4.
So do they give that?
I'm going to go down, down, down. Yeah, they'll always give you the mean and the standard deviation.
Oh.
So you can create the picture from that. Yeah, so they'll always be given to you. That was a good question. So along this normal curve, this is called a standard normal curve. And a standard normal, which I have on the front of your notes that I just passed out to you if you want to look at that really quickly. A standard normal curve means that the mean is 0 and the standard deviation is 1. And the reason why we have something called a standard normal curve is, for instance, if you take the SAT and the ACT and you get a 1350 for the SAT and you get a 29 on the ACT. Those numbers do not correlate together. Like, I don't know how they compare. Like, which one did I actually do better on? Because a 29 is a lot less than a 1350 just points-wise, right? But a 29 could be way better than a 1350 when you compare the two. So what people will do in order to decide, like, which one did I do better on, is they take both scores and they create a z-score that essentially takes both scores and puts them on an even playing field. Like, if you had a z-score for both of them, then they would translate to be able to be comparative on one graph or on one normal curve. So that's what a z-score is it tells you how many standard deviations you are from the mean. So if you had a z-score of, for your SAT, if you got a z-score of 1.4 for the SAT, and you got a z-score of 1.6 on the ACT, then you would actually have done better on the ACT than the SAT. So what it does is it takes two different things that have numbers have nothing to do with each other and translates it to be one common graph that you can actually compare them. This is the formula. You do need to have this memorized.
So what would you put into that formula from the SAT score?
So we're going to look at an example in a minute, and it doesn't use the SAT-ACT example. It actually looks at two different classes that have different averages and seeing like which one was better. Because if you have a lower average but you did worse, if you're still above average compared to another class where you're below average but you did better, then you're seeing like comparatively or relatively which one did you do better on. So not just the points, but compared to everybody else. Another way to write this instead of value minus mean over standard deviation is z equals x minus mu over sigma, like that. Mm-hmm.
So is the difference between like for the ACT SAT example, like you said they got like a 29 and it would be out of like 34 or something, and then it would be like 1350 out of 1600. What's the difference between comparing those two under this? Like if you did like the percentage, like 29 out of 30. for
Because it's comparative to how everyone else did. Like relative to the percentiles of other people.
Oh, so it's like if you did better on your ACT than someone did on their SAT?
Yeah, because that's how those scores are created, is basically how well did you do compared to everybody else. So if I were to look at these z-scores, if it will pop up, there we go. How would so if you have a negative z-score, what does that mean?
You did below average.
Yeah, you did below average. So this person is 2.3 standard deviations below. 1.8 above, 4.3 below. So if you have a negative z-score, that means that you are below average. If you have a positive, that means you are above average. And those numbers tell you how many standard deviations you are above or below the mean. So here's an example of looking at, and this could be an example for you in your own classes if you've taken 2 tests and it's asking which one did Sally do better on. Because in your mind, you're like, points-wise, I think I did better on the first test than the second one. But you have to think about it comparative to the class average. Which one did I actually do better on? So in order to compare these 2 test grades, I need to find the z-score for both of them. So looking at test A, the mean was 56. I'm going to circle that number. And standard deviation was 3.5. And she got a 62 on it. So her z-score on test A would be what she scored, which is what? 62 minus the class average over the standard deviation. So 62 minus 56 over 3.5. So what is her z-score for test A? 1.714. And then her z-score on test B, she scored a 69 minus the mean was a 65 over 2.8. So what was her z-score on 1.42, what? 9? So looking at her z-scores, which test did she do better on? The first one, but score-wise, if I'm just looking at the points, she did better on test B. She got a 69 compared to a 62. But relative to what the class average was, she actually did better on test A. So what it's doing is it's taking 2 sets of data and putting them on a universal scoring or scale.
Why would you do, like, other than for standardized testing, why would you do this?
Just looking at 2 different sets of data, and standardized testing is the best example I can give you, but just looking at 2 sets of data that don't have the same scale and putting them together to compare them is essentially what it's doing. The next thing is talking about percentiles, which we already did, but percentile is just the value that's at or below. At or below. So when you're given a percentile on a SAT or ACT, that means you're at or below that percentage. So you did as well as or below 80%. So this example is talking about, I think this is a very interesting example, but talking about baby's head circumference. And looking at, because you know when you go to the doctor at the pediatrician and they give you your height and weight percentile, they can also give you your head circumference percentile. So, what percent, and the bottom is the percentile, so what percent of newborns had head circumferences greater than 37? So what percent had greater than 37? 25%. Because 37's at the 75th percentile, so 25% are above that. 25% had bigger than that. And then this question kind of goes backwards. So it says 10% of newborn babies had head circumferences bigger than what value? So what percentile would I look at there?
90.
The 90th. How come? Because it's 10% or above that. So at the 90th, be 38.2 centimeters. Okay, what I want you to do next is go to the notes that I passed out to you, because I'm going to show you how to do this on the calculator. So the first types of questions will just ask you about standard normal distributions. And standard normal means what? How do I know something is standard normal? The mean is what? The standard deviation is what? 0 and 1. So the mean is 1, the mean is 0. Standard deviations are all 1. So that's when you are given a z-score, like z equals this. And so if I wanted to find essentially what we're calling the area under the curve, like what percentage is greater than 1 z-score or something like that, I am going to use the function in my calculator called normal CDF. Okay, so if you're given z, on my normal curve, that would fall, if this is 0, 1, 2, 3, 2.45 would fall somewhere like around here. So I want to find the area greater than 2.45. So in my calculator, I'm not going to show you this because I'm just going to give you the buttons. You're going to go to second, vars. So everybody hit second, vars, and then the normal CDF button. So vars is located under the down arrow.
Oh, there.
Second vars, you just hit vars. There you go. Normal CDF, which is option number 2. Not PDF. We don't ever use normal PDF, okay? So normal CDF. From there, it's going to ask you for a lower and an upper bound. Lower means the one that's on the left, and then upper means the one that's on the right. So if I want bigger than 2.45, then I'm going to write, the way we show our work is showing what we typed in the calculator. So it is normal CDF. My lower bound is 2.45. My upper bound is how we're going to represent infinity, which is a really, really, really big number. The way that I write infinity is saying 2 to the 99th power. That is my infinity. Sometimes it'll automatically set to be like 1e99 or something, and that's the same thing as saying 1 times 10 to the 99th. I just always stick with 2 to the 99th. And then your next places, it asks for the mean and the standard deviation, which in this case are what and what? 0 and 1. And then hit enter. So it goes lower, upper, mean, standard deviation. Yeah, looks good. Yeah, use the caret button for the 99th. And what do you get for your answer? 0.0071. Go out 4 decimal places. Okay, so this next one, it's asking for values less than 0.039. So if I were to label 0.039, it would be pretty close to the mean, right? Pretty close. And I want the values less than that. So I want to find everything below 0.039.
What did you just find with that first one?
I found the area or the percentage above that z-score. So there are 0.71% of people that fall above 2.45. Yes.
What's the one?
The standard. So it goes lower, upper, mean, standard deviation.
So this one, do we just flip the upper and lower?
So this one, I'm going to flip it. So I'm going to say normal CDF. My lower is now going to be negative infinity, which would be negative 2 to the 99th. My upper is going to be what? 0.39. My mean. And my standard deviation, 1. Good. So what did you get for that one? You should get a pretty 0.65. 0.17. Good. Which makes sense because it's over 50%, right? It's right at the mean. Anything above or below that is 50%.
I got negative 0.348.
You should not get that. You should never get a negative answer for area.
Thank you.
So then for C, try C. Because it gives me a lower and upper bound. So I'm just finding the shaded area between. I don't need any infinities for C.
Do we always go out 4 places for
3 on each side. So this one's between negative 0.25 and positive 0.25. Uh-huh.
How do you know which one's the lower bound and which one's the upper?
It goes left to right.
So like the negative one.
So if it's shaded all the way to the left, then I'm going to do negative infinity as a lower. And then if I am shading all the way to the right, then it's positive infinity for upper.
But since we don't have an infinity on this one, if like the negative number will be the lower bound.
Uh-huh.
And it's always going to be 0 and 1.
It is for standard normal. So when you see this Z right here.
Is there a non-standard?
Yes, we're about to do that one.
Oh, that's fine.
So what did you get for this one?
0.1974.
1974?
How
Good.
many should we go out?
4.
4?
Yes.
Wait, is it 3 or 4?
4.
4?
Yeah, for this do 4.
For this, it's 4.
Just you can always do 4 if that helps. Okay, I'm going to skip D because I'm confident in that. Now, if it asked you for a percentile, you're going to use what we say is inverse norm. So for area under the curve, normal CDF. For percentiles, it is inverse norm, which is second vars, and then I think it's option 3, inverse norm. So what this is asking me is, it's saying how many z-scores are below, or what z-score is at the 60th percentile. So the 60th is right here. So basically, what is that z-score? So to find that, I'm going to type in inverse norm, my percentile, which is 0.6, my mean, which is what?
0.
And my standard deviation, which is 1.
And tail.
Wait, do you put in the 0.6 for the area?
Uh-huh. The area is your percentile. Just leave it the way it is. If you have a newer 84, like the CE, you're going to ask for the tail. Just always leave it as left, okay? So what do you get for that?
0.2533.
2533. So that means when the z-score is 0.2533, you're at the 60th percentile. I'm going to skip F. We don't really need one like that. And I'm not going to do G, but if it said top 10% of the data, what percentile would that be at? 90th. Okay, so let's skip down to whenever it's not a standard normal. So something where it's a word problem and it's actually giving you the mean and the standard deviation. The only difference is now you're not putting in 0 and 1, you're putting in whatever it gives you, okay? Yes, it will. So assume the heights of college women have a normal distribution. That is important that it tells me normal, so I'm going to underline that with a mean of 65 and a standard deviation of 2.7. What is the probability? That just means area under the curve. What is the probability that a college woman is 62 inches or shorter? You don't have to draw a picture, but if you want to help you, then you can. But what would my normal CDF look like? 62 inches or shorter. So what would my lower bound be here? Negative infinity to what?
So even though there are gonna be no women that are negative,
I just always use negative and positive whenever I'm thinking about the shaded area. I'm sure if you put 0, it would still give you the same answer, but negative and positive infinity just get you the exact answer. Okay. So what's my upper bound? 62. What's my mean? 65. What's my standard deviation? Good. So what do you get for that? 1333. Okay. And this is how I would want you, like this is showing your work, telling me what you typed in the calculator. And going out 4 decimal places, box your answer.
do we need to have like a unit for this?
Nope, because this is asking you for probability or proportion, percentage. So leave it just as a decimal.
So now, do you not put like inches or anything?
Yes.
So is the one on the board not normal because
It was normal and just wasn't standard normal. Okay. Okay, let's jump down to one percentile question.
what makes it not standard?
The mean is 0 and 1 for standard. And not standard means the mean and standard deviation are something different. So let's look at number 4. Got 1 minute, so I'm just trying to get through it, okay? Number 4, it gives me a mean and a standard deviation, and it asks me for the 75th percentile. So what would I do here?
Inverse norm.
Inverse norm. What's my area? 0.75. Mean is, and standard deviation is. Good. So what do you get?
126.74.
Perfect.